Imagine you have a terabyte of web pages. You want to count how many times each word appears. The logic is trivial. A first-year student could write it in 10 lines. But now imagine running it. One machine will take days. So you split the work across 1,000 machines. Suddenly you're writing code to partition data, schedule tasks, handle machines that crash midway, retry lost work, and shuffle intermediate results across the network. Your 10-line word count has become 10,000 lines of distributed systems plumbing. This is the problem Jeffrey Dean and Sanjay Gamawat set out to solve at Google in 2004. They had hundreds of engineers writing these large-scale computations, building inverted indices, analyzing crawl logs, computing web graphs, and every single one of them was rewriting the same distributed systems machinery. The insight of MapReduce is that almost all of these computations follow the same shape. If you can capture that shape in a library, the plumbing only has to be written once. So what is the shape? Two functions. The first is called map. It takes one input record, say, a document, and emits a list of key-value pairs. The second is called reduce. It takes a key and all the values that were emitted for that key, and combines them into a final answer. That's it. Map fans the data out into labeled pieces. Reduce collects everything sharing a label and folds it together. Let's ground this with word count. The map function receives a document. For every word it sees, it emits the pair, word 1. So the document, the cat-sat, produces 3 pairs. The 1, cat, 1, sat, 1. Now the library does its magic in the middle. It gathers every pair that shares a key, so all the 1 emissions from every document across the cluster get bundled together. Then reduce is called once per unique word, with the full list of ones. It sums them. Out comes the final count. The user wrote 2 tiny functions. The library handled the terabyte. The same shape covers a startling range of work. Distributed grep? Map emits a line if it matches the pattern. Reduce is the identity. Reverse a web link graph? Map emits target source pairs for every hyperlink. Reduce concatenates all sources pointing at each target. Building an inverted index, the core of a search engine? Map emits word document pairs. Reduce collects the document list for each word. Sorting a terabyte? Map extracts the sort key. Reduce writes records out in order. The same 2-function skeleton, wildly different applications. Now let's look at how the implementation actually runs on a cluster. When you launch a MapReduce job, the library splits your input into pieces, typically 16 to 64 megabytes each. It then forks copies of your program across hundreds or thousands of machines. One copy becomes the master. The rest are workers. The master's job is to hand out tasks. It has mmap tasks and our reduced tasks to distribute, and it hunts for idle workers to give them to. A map worker reads its assigned input split, runs your map function on every record, and buffers the emitted key-value pairs in memory. Periodically it flushes them to its local disk, but not into one file. It partitions them into our separate files, one per reduced task, using a hash of the key. The worker then tells the master where those files sit. The master forwards those locations to the reduce workers. A reduce worker pulls its assigned partition from every map worker's local disk over the network, sorts the data by key so identical keys cluster together, then calls your reduce function once per unique key. Output goes to a final file in the distributed file system. Now the critical question, what happens when a machine dies? In a cluster of thousands of commodity PCs, failures aren't rare events, they're routine. The master pings every worker on a regular heartbeat. If a worker stops responding, the master marks it dead and reassigns its tasks. Any map task that was completed on the dead machine has to be rerun, because its intermediate output lived on that machine's local disk and is now unreachable. Any in-progress task on the dead worker is reset to idle and picked up by someone else. Reduce workers that were about to read from the dead machine are notified to read from the re-execution instead. The authors describe a real incident where network maintenance took 80 machines offline at a time for several minutes. The MapReduce job didn't fail. The master simply rescheduled the missing work and the computation finished. This is the payoff of the restricted programming model. Because map and reduce are pure functions of their inputs, re-executing a task is always safe. Fault tolerance falls out of the design almost for free. The first big idea was fault tolerance. The second is locality. Network bandwidth inside a data center is precious, much scarcer than disk bandwidth. The input files already live on the cluster, replicated 3 ways across local disks by the Google file system. So the master doesn't schedule map tasks randomly. It looks at where each input split is physically stored and tries to place the map task on a machine that already holds a copy. Failing that, it picks a machine on the same network switch. The result, for large jobs, most input data is read from a local disk and never crosses the network at all. The third big idea addresses stragglers. Near the end of a job, one slow machine can hold up the entire computation while everyone else waits. A flaky disk drops read speed from 30 megabytes per second down to 1. A misconfigured machine runs 100 times slower than its peers. The fix is elegant. When the job is close to done, the master launches backup copies of the remaining in-progress tasks on other machines. Whichever copy finishes first wins, the others are discarded. It costs a few % extra compute. And it saves enormous time. The authors show that disabling backup tasks makes their terabyte sort run 44% longer. Let's talk about how MapReduce actually performed. The authors ran 2 benchmarks on roughly 1,800 machines. The first was grep, scanning a terabyte for a rare 3-character pattern. It finished in about 150 seconds, with data being consumed at peak rates of over 30 gigabytes per second. The second was sorting a terabyte, modeled after the TeraSort benchmark. It completed in 891 seconds, competitive with the best reported result of the day, and written in under 50 lines of user code. The most striking result is the failure experiment. The authors deliberately killed 200 out of 1,746 worker processes several minutes into a sort. The cluster scheduler restarted the processes, the master reassigned the lost map work, and the job finished in 933 seconds, just 5% slower than the failure-free run. Losing more than 1 in 10 workers cost almost nothing. That is what fault tolerance built into the framework buys you. The impact inside Google was enormous. In August 2004, roughly 1 year after the library stabilized, Google ran nearly 30,000 MapReduce jobs, processing over 3 petabytes of input data. The number of distinct MapReduce programs in the source tree grew from 0 in early 2003 to nearly 900 by late 2004. And the production web indexing system, the pipeline that turns crawled pages into the data structures behind Google search, was rewritten on top of MapReduce. One phase of that pipeline shrank from 3,800 lines of C++ down to 700. Pause on this for a moment. Try to picture writing your own distributed word counter from scratch. You need a task queue, a heartbeat protocol, a retry mechanism, a shuffle implementation, a checkpointing scheme, and a way to detect stragglers. Now imagine none of that existed as a library. That is the world MapReduce ended. The lesson generalizes beyond this one system. The deeper insight the authors landed on is this: restricting what programmers can express is a feature, not a limitation. Because map and reduce are pure functions, the framework can freely rerun them, reorder them, replicate them, and move them close to the data. A more expressive interface would give programmers more power and give the framework less. The bargain right in this narrow shape, get 1,000 machine cluster for free, turned out to be one of the most productive trades in the history of systems software. It seeded Hadoop, Spark, and essentially every modern big data engine that followed. You just walked through a paper that reshaped how the world processes data. Next time, how do you actually store petabytes across thousands of unreliable disks so that a system like MapReduce has something to read from in the first place?